Hey folks, we'll at least informally get started in the meantime. Here's just some info if you'd like to scan this QR code or follow this link to find out more about all the educational programs that are ongoing, happening now and ongoing in the future, including an entire week on AI medicine in early June, so be on the lookout for that. Before we formally introduce our guest speaker, who we're very privileged to be with, for some context, here's my Google Scholar page. I don't know if I am proud, my top most cited paper by far was a 2-page perspective piece I wrote as a fellow. Okay, I work on a research project for a year, nobody cares. But look, it's 1,000 citations. Like, that's pretty impressive. Yeah? No? That's pretty good. That's pretty good. For context, this would be Robert Tibshirani we're about to hear from. 85,000 citations for one of his pieces of work. 64,000 for a solo author piece in 1996, and the list goes on. So with that kind of context in mind, really, we are in the presence of a legend here, and are very grateful and privileged to speak to Rob Tibshirani. So, Rob, if anytime ready, you go ahead and stand to the podium so we can see it. And first, before we dive into the science, I know you have new innovations to tell us about. Tell us just about yourself for a bit. Who are you? Where were you born? Where'd you grow up? How did you end up studying the things you're studying?
I'm from the 51st state. I can't do it. We're not going to do it. I grew up in Niagara Falls, Ontario, and Toronto, and went to school for Waterloo undergraduate, master's in Toronto statistics, and then came here to Stanford in '84.
As a
81.
As a student or faculty, or is that?
PhD, my PhD here.
Okay.
Undergrad up.
Oh, wow. Okay.
I graduated in '84, and then I went back to Toronto for 12 years as a professor there, and then came back here, professor in '98. How did I get into this? Well, my wife, fiance, and my wife was a doctor, so I got interested in medical things, but I also love math, so it's kind of a natural place to travel to, statistics, biostatistics. So I've always been interested in the applications of statistics, especially in medicine.
Was that a very deliberate purpose that you made that application part of your focus, or is it just the tools, the technology, the methods you develop really have applications anywhere? Just this could be one of many you could apply them to.
That's true, but I guess I've always felt I'd rather be, I'd feel better if I did something for public health than financial markets, for example, so.
Fair enough, fair enough. I think many in this room and online have a common view and are glad to be here. If you'd like to go ahead and share slides, and let's go ahead and dive in.
Okay, thank you for having me here. We'll make this informal, so pretty much be a group, and please ask questions during the talk. I don't have that much material that I need to go at 100 miles an hour. I don't plan to. So this is very recent work, not published yet, called Univariate Guided Sparse Regression. So it's kind of a new lasso with has some, I think, some interesting properties. It's a joint work with Trevor Hasty, who you know of. He's been my class. He was my classmate back at Stanford as a PhD student. We actually started working as students, and we worked together ever since. And Saurabh Chatterjee, who was a colleague in statistics, he's actually a probabilist. The first time I've ever worked with Saurabh. These are the two homes of statistics. This is the older home, Sequoia Hall, where I still am, and actually the older faculty. He's going to split the two. The older faculty stayed. We have a choice, and the newer faculty went to the new Coda building right across the street. So if you haven't seen the Coda building, it's really beautiful. It's on top here. There's an incredible conference room on top. It looks like a spaceship. Stained glass. Amazing. So we're in both buildings. So yeah, these are actually the Sequoia Hall. My neighbors to the left and right are Saurabh and Trevor. Trevor and I have written a lot of work, done a lot of work together. Saurabh, never worked with him before. He's really a mathematician, but I wandered into his office one day about 4 months ago, and I said, I've got this thing I'm working on, maybe you could prove something about it. And boy, he's really something. You meet a real mathematician. Like, I'm okay at math, pretty good. A real mathematician is like reading, like you play basketball and you meet LeBron James. This is like it's a different level. He's a different level of mathematics. So anyway, I'll touch upon what he's done. But if you like math, you want to read the details. Okay, so this is about the lasso, which I'll just review in one slide, actually. So it's supervised learning, using a linear model to predict y from x. And the lasso says, well, let's start with least squares. Least squares is great, it's been around for a long time. Least squares is limited, right? Because, for example, the number of features exceeds the number of observations, you interpolate, and the solution is not useful, right? It's a singular system. So the lasso puts a budget, I think this is a budget, on the sum of the absolute values of the coefficients. So it says, go minimize this sum of squares, but you have a budget on how much you can spend on the coefficients. But the thing about that, you don't shop. You try to predict y with the most predictive features, but you've got to pick and choose which ones to use because it's budget. The budget's very big, you'll just get least squares again. As the budget gets tighter and tighter, what it does is it forces some of the betas to zero. Namely the ones that are not very predictive of y. So it's trying to choose the most predictive features and zero out the other ones. In the budget, it chosen typically by cross-validation. We leave some data out, we fit this lasso from many different budgets from small to big. We choose the one that for the validation set, which does the best prediction. Okay, so that's the lasso. Well, it's usually written in Lagrangian form, but that's what's more convenient numerically. But when I think you describe it, it's the budget I find appealing. So, why is it attractive? Well, this penalty gives you sparsity. It gives you exactly zeros on some of the features if it's with a tight enough. So it selects features for you, which is great. It's convex. For those who know about computation, that's a tremendous advantage for computation. It means we can solve this problem for very large data sets. Exactly. Convex has a unique solution. And we have a practice called GlimNet, which you probably heard of, which is used actually very widely. Written with Jared Friedman, Trevor, and many others. It's still evolving. And, it's a very fast package which solves the lasso not just for least squares, but for the whole GLM family and survival models and lots of goodies. And very recently, there's a new package called Adili in Python by Trevor's brilliant student, James Yang, which is a Python version of GlimNet and more. It does, so it's just like GlimNet, just as fast in Python, but it also does group lasso. That's a situation where the features are predefined into groups, which is computationally very challenging, but he's found a very, very clever way to solve it. So if you're a Python user, I would look at Adili. This is all the online. You can interrupt me anytime. This is sort of a brag slide over this is GlimNet, which is an R package. We started about 13 years ago, and it's up to about 8 million downloads, and seems to be actually accelerating. So it's very, very widely used, and the deal has only been around for 6 months, and it's already getting a number of downloads in Python. So Python is getting more and more popular relative to R. So there's a lot of activity. Okay, so what am I talking about today? Well, sort of it's a new lasso called a univariate guided lasso, or UniLasso. So this slide will motivate the idea. So this is a typical example of two-class problem. I've got patients healthy and 60 and some with cancer. We're trying to classify the patients on the basis of 550 protein biomarkers. They're actually the heights of peaks on it from the mass spec. And this is a typical problem. I'm not giving much detail because this is unpublished data with a collaborator who doesn't want to say much until it's published. But what I have here at the top is that the model is chosen by cross-validation for the lasso using cd.gradient. So it chose 12 biomarkers out of 500 or so, and with these coefficients. And it did quite well on the test set. We had a separate test set. It got about 95% correct in the prediction. Okay, and down here is a model chosen by UniLasso, which I'll introduce in a few slides. But I just want to contrast and motivate things first. Yes.
Can you maximize your screen? It's just easier for people online to see the text.
The green button.
Oh, I'm sorry. I see. Maximize the screen.
And then we have microphones in the roof, basically, which there's a little bit of background noise. If you just speak up a little bit, it'd be easier for people online.
And now I didn't mean to get 2 per slide. How did that?
I think you can do Command L.
Command L.
Yes. So first you have to exit out and then.
not back there for a bit.
Oh, this is not active.
Yeah,
Sorry. text.
I can go to preview maybe or something.
Yeah, if you go to preview or something, you may be able to do it as a.
Let's do. It's preview. This is. Oh, sorry, wrong file.
You want the PDF?
Let me get a PDF.
Third one, third.
Okay.
You got talk new, you got talk new 2,
Preview.
Yeah,
talk new 3.
Okay,
and then Command L, I think that's full screen.
no.
That
turns
No, there is a presentation somewhere,
Enter full screen.
entire full screen. Slideshow. No, the second one from the. And then the second one from the bottom, slideshow. There.
The second slide would be okay. There we go, we made it.
Okay, so, that's good size or bigger? Or-
And-
That's as big as I can get.
Good enough, just describe what we're thinking
So
about.
talk louder. Okay, so, anything else? Okay, so this is the Lasso model, it was chosen by using cross validation. And produces, it chose 12 biomarkers, I just numbered them 1 through 12 out of over 500. And it was quite accurate in the test set. Okay, and this is the UniLasso model, which I'll again describe. I'll describe how we get it in a few slides. I want to contrast them. I've also put the univariate coefficients alongside here, but of each of these biomarkers. And you see something that we see fairly often in multiple regression, also Lasso, is that there's a sign change. Right? This guy was negative on his own. So it means protective in this setting, so you're less likely to have cancer. But then in the multivariate model, it's extremely, it's bad. It's got a much higher correlation, negative correlation with, lots of correlation with cancer. So it's bad to have that. And this guy, number 7, is the other way around, right? He's bad on his own, but apparently very protective in combination. So, we see this quite often, and we tell students or collaborators, I tell them, well, sorry, that just happened. Right? That means correlation. Correlation, all bets are off. You can have these sign changes, right? But it's never very satisfactory. It's hard to, it's not very satisfying. It's hard to explain. Hard for people to accept it, but it's just a consequence of correlation. Okay. The UniLasso model, which I'll can describe the algorithm in a few minutes, it does not allow sign changes. It explicitly says the sign of this guy is going to be the sign of the univariate. So if you're negative on your own, you're negative in the multivariate model, and vice versa. Okay? Now you might not like that, but we'll see where that goes. But some more points here. These models actually, this model also has about 95% accuracy. But the models are very different. I label these 1 through 12 and A through G. We only share 2 biomarkers. I've kind of hidden that, but here they are. 2 and 6 are the same as B and C. Otherwise, they're all different, which is kind of surprising, right? Because I don't know about you, but when I feel more like the Lasso, I think, yeah, I got a model. This is great. This is the best model. It's got all the right predictors. Like you think it's special somehow, right? And it is the unique solution to the Lasso. But we see here an example where 2 very different models, very different parts of model space are giving a similar performance. So that's kind of it's kind of worrisome. And it's surprising, maybe, right? So, but that, yes.
Isn't there, I think in Brad Efron's paper, the prediction estimation attribution, he shows an experiment similar to this where if you have, say, 500 biomarkers, you find a model, take out those 12, it will pick another 10 and gives you roughly the same performance. It keeps going for like 3-4 turns and it still works.
I think that's like with random forest, but yes, exactly the same point. There's a lot of redundancy with correlation, right? Nothing's special if there's correlation. You can.
But that's the underlying biology, because you are picking, say, 12 biomarkers that represent the highest change for a given biology. But when you take those 12 out, the next 6 would also represent the same biology. That's where correlations might be coming from.
When you say it's underlying biology, it says the first set's underlying biology, not the second set. the truth is you don't know what dynamic biology is, right? It's like, right? If you have five biomarkers that are very highly correlated, you can't tell which is true biology and which isn't, right? So,
No, that's right, it's the same biology, but it's coming from the same immune cell type, for example.
I see, yeah, fair enough, right?
I think maybe what he's trying to say is if there's been a previous association between those biomarkers, for example, inflammatory proteins,
Yeah.
then maybe that's perhaps what you're trying to say.
If you have prior knowledge about what really is going on, you could untangle this more. Okay, but so the first overarching point I'm making is that in these kind of high dimensional feature selection problems, there's a lot of different models, very different from each other that have about the same performance. So let's just keep that in mind whenever we go. And that's true of Lasso or random forest or whatever you're doing, right? So, model search in a high dimensional feature space is difficult, right? And we can't pretend like we found the best solution every time. Second point is this. I'm going to try to argue that this UniLasso, which I again haven't defined what it is yet, has got some good properties. Like, for example, it's got fewer biomarkers. And we'll see in general that this new Lasso is actually gives you much more sparse, much fewer biomarkers, like half or two-thirds, depending on the problem, which I think is good.
How did you do that?
How do I do what?
How did you go from all of those biomarkers? You applied,
Can I get this table here?
yes.
I'll tell you.
Oh, thank you. I was immediately I started thinking.
There's an algorithm. Yes.
That was it.
Is there any requirement for the sample size by using the UniLasso?
Well, yeah, you've always got requirements for sample size. Well, I mean, requirement for sample size, the more data you get, the more accurate your predictions are. So there's no formal requirement, but like any other supervised learning method, the more data, the better. And you can tell by, for example, your error rate if you have enough data. Like if the error rate's very poor, maybe you need more data.
So it doesn't require the number of bits much.
There's no different requirement in the Lasso. It's just a different way of. I'll get to it real soon. I want to just again motivate you someone. Is there any other reason you might prefer? Well, maybe I'll say more generally. Another important contrast between this model and this model. We have the sign changes as the first thing. There's something else that's quite striking. Two of the univariate coefficients. They're bigger, right? Okay, so is that good? Well, I think it's good. I think it actually means the model is more stable. I think of it this way. Suppose you're putting together a basketball team, like all the Warriors, right? Here, this guy on his own, he's not a very good player, really, right? But you only got on the team because he's got the right chemistry with the other players. The same with this guy, right? But this team is put together, only about the negative sides. It's a bunch of stars put together, and as long as they can work together reasonably, they're going to, you have more confidence in that team. Now that's just a loose analogy, but the point is that, if something has a strong univariate effect, all else equal, your prior would be that it also has a strong multivariate effect. Okay? And the whole theme of this method is that we're going to sort of use as our, what's the word? Well, we're going to hold on to the univariate strength as a pillar, so to make the model more robust. So I'll show you in a few slides that in a quantitative sense, this model is more robust than this one is. And it's because the coefficients are larger, the univariate coefficients are larger. Okay, so you guys are itching to see the algorithm. Okay, so this is the outline, but I probably won't get to all of it, that's fine. So what we want to achieve is, I've already said, the signs of the final coefficients need to agree with the signs of the univariate coefficients. So, or they can become zero, that's fine. But also features with larger univariate coefficients should be given a boost in the final model. It's like a prior, saying, if age, for example, is predictive of Alzheimer's, which it probably is, on its own, very strongly predictive, then the multivariate model with many other features, and it might not be significant, but all else equal, you kind of expect it to be. Or you'd like it to be, right? To make the model more interpretable. I say caution because, this requirement is sort of sacrilegious to statisticians, or because if we teach the fact that you can get sign changes, now I'm saying, well, we're going to rule them out. Well, let's see where this leads. Like, does it really hurt? Maybe it helps. That's sort of the theme. Okay. So here's the algorithm. It's actually quite simple. It's just on the one slide, although we're going to make one change on the next slide, but here's the thing with it. You can compute the univariate least squares coefficients of y on each feature. Slope, the intercept and slope. Okay? So the bigger the coefficient, the more stronger that feature is. And then what happens? We take these coefficients and we use them to scale features. It's like changing the units, right? If we're starting out in age and years, and all of a sudden I change age to days, that changes the units of the x. And the beta, this beta can, if the point here is, let me just, like, we scale the coefficient, we scale the features with these things, and then we fit a lasso now. Here's the new parameters, theta, with non-negative constraints. So what's going on here? Well, the non-negative constraints are what would get the no sign changes, right? Because I start with something, let's say beta hat j is positive, multiply it by a non-negative number, I can't change the sign, right? Similarly, if it starts off negative, it stays negative, or maybe zero. So this constraint gives us the no sign change. This guy, multiplying the feature, scales up the feature and gives preference to things which are stronger on their own. This is changing the units, that's the way I think of it. But they have to compete with each other for this pendulum. So if I change the units, it's not by making it by multiplying by a large number, it's going to only require a small theta now to enter that variable. So it's that simple. We scale the features by univariate strength, and we do a non-negative lasso to keep the signs changes. The signs unchanged. Okay. Very simple. Computation, very simple, but actually doesn't work. Doesn't work because we overfit. The reason is we've double dipped. Right? The y is we use the data at both steps. Y here and also here. So by the time we get to step 2, there's a lot of leakage of information from the first step into the beta hats. So this overfits back. So what's the fix? The fix is to use the leave one out slope intercepts. Right? So what does leave one out? This means we leave out observation I and for the jth feature. And that's the regression of y on the jth feature without the observation I. We do this for each I and j. This is actually, it's a whole matrix, right? It's actually n by p, just like the data. Looks like a lot of work, but there's nice computational formulas that allow us to do this very quickly, both for linear models and GLMs and everything. Okay? So now we just put those guys into the second step, and that's it. That's the UniLasso algorithm. So what that does is that this kind of internally, this first step is now sort of internally validated, right? Because we've left out data points. Each data point doesn't get to say anything about the slope, and that point is left out of the I row here. So that's it. This is the most important slide because this is the algorithm. And now we're going to talk about its properties and examples of when it works, when it doesn't work. So just leave one out slope and intercepts, scale the features, and do a non-negative lasso. And at the end, we get coefficients which are theta times beta. And here they are. So the model comes out, it's another sparse model. Look like the lasso. Actually, you'll see it's usually far sparser, okay? Which is probably good. Right? We saw in the first example, it was something like 13 versus 7, well, typically, or 8, whatever it was, but it's usually considerably sparser than the lasso. The lasso tends to pick, most of the right predictors, but then add some noise, get some false positives. This guy's much better at honing in on the right ones and lead to a sparser model. Yes.
If you just do the leave one out intercepts, get the univariate coefficients, rank order them, and pick the first 6 or first 5.
No, because they still correlate. The reason you do multiple regression is that there are correlations, and you have to, it's not like the top 5 or 6 are the best 6 because there's correlations. Well, you said it would work exactly correctly if the features were uncorrelated. But,
like in my examples are all just immunology, but if there was a one cell type that is driving the disease, your top 5 or 6 could be coming from the same cell type and they don't give you any new information.
So that's a good point. So this would hopefully pick one of those and then other stuff. We're going to stare at that for another minute if you want. So again, I'll talk about software the very last slide. There's if you use GlimNet, there's a package called UniLasso, which is just like GlimNet, same form. In fact, it produces a GlimNet object. So all the plotting and everything is there. It's really the same form. There's just one more step. It's just this screen, this step here, where we can keep these one intercepts and slopes, and then it's just an application of GlimNet. It's all very fast and computable.
Did you say that you've not published this yet, or have you published?
It's on archive, but it's not
Okay.
published in the journal.
Okay.
I'll give you the reference to that later.
Appreciate it.
Okay, so I've said some comments. I said the first thing that this use of leave one out in the first step is really crucial. Without it, the method is badly overfits. This applies to all generalized linear models. They're covered by GlimNet and the Cox model, lots of goodies. We've heard of stacked regression in machine learning. This is a special case of it in the sense that stacked regression, you start with learners like neural networks and boosting and manifold, and you take a weighted average of them. This is a stacked regression, but the learners are very simple. They're just univariate regression. Right? So it's a very sort of extreme case of stacked regression. Okay, well, let's see 2 examples, one good, one bad. So the first one is like a contrived home court for this method. Right? Like, well, what's the ideal simulated data for this method? Well, I think this is it. I think I start with a feature matrix X. Actually, I here pick my ID, and I generate in a beta, which is sparse. I think it's like 20. When I say 20% sparsity, generate a Y. I take that Y and I compute univariate coefficients, and then I generate Y again now, but multiplying the coefficients by this guy. Because this is the very model that we fit in the second step of UniLasso. So this is a real setup. If it doesn't work here, I better pack it in, right? But it does work. What does work mean? Compared to the lasso, here's the mean square error. The test set is far less. No, it's just over half, and it's got smaller support. Okay, which means that support means the number of features it picks. And then, as you'd imagine, the true positive rate and the false positive rate are better, right? 63 versus 49, 51 versus 37 versus 51. So, I mean, it's a setup. So, as you'll see, I'll have this one slide sort of summarize the simulations. This is sort of the general picture we see is that the predictive ability of the two are both the same. Sometimes UniLasso is a little better, a little worse, but the support is far less. The UniLasso. And I've got some evidence that you'll see that it's more robust. It's harder to break. Okay? But I need to talk about a counterexample, right? Which is what the statisticians would mainly complain about. Here's your typical example. You've got 100 observations, 20 features, 2 positive correlated features, but their population coefficients are the different signs, right? That's exactly the thing I ruled out. And the method is disastrous there. We have to get twice the error of lasso or linear regression. Okay, but the good news is you have cross-validation to tell you this. Right? So in any given problem, you run lasso, you run UniLasso, you look at the cross-validation error. And it reveals that this is not a good example for UniLasso. Okay. We know methods of panacea for all problems, right? Someone tells you they have that, I wouldn't believe them. So, but that's sort of your expected counterexample. Okay, so I made this claim that UniLasso somehow was more robust, that Lasso might be more brittle. Here's a way of trying to examine that. In machine learning, they have something called adversarial attacks. So the deal is you have your training data and you have your test set, and we normally assume the two are from the same population, right? That's our sort of framework assumption. But of course, in practice, that's never the case, right? The test data may be different university, different hospital, it might be taken a year in the future. For many reasons, there's data drift, right? So we have to care about whether our algorithm is robust to change in the test data. So the ML community has this nice idea about adversarial attack. which says, well, you take the test data and you add noise in the direction of the gradient. The gradient is the equation that you solve to get the solution. And you can show that that's sort of the worst case. That's the most sensitive point. You want to break the method, that's the pain point right there. I did that for the first example with those two classes. I created training and test sets at random 50 times. Each of the methods got the same training set. And then the test sets, I added this bad noise to each of them. It's different bad noise because each one has a different gradient. So each noise is designed to make that method break. And this is the result. Here's the test set AUC. This is the level of noise that I added here. And with no noise, UniLasso has an AUC about 10% higher. Then as you add more and more noise, Lasso breaks much more quickly, right? As opposed to UniLasso, which of course eventually breaks, but it's more robust. And why is that? Well, my theory is that Lasso again is sensitive to correlations. It's using X transpose X directly, right? So when you add noise in the feature space, that messes up the correlation. So it's not surprising it's going to fail. UniLasso also uses that correlation, but also uses the univariate strength, which is, it's not going to change very quickly when you change the correlation. Eventually it will, but so again, it's if you tie yourself to the univariate strength, you get some security, get some robustness. We see that here. Okay, so that's, and the theme of this is that the overall theme is that model search in high dimensions with lots of is difficult. It needs some help, some guidance. So I'm choosing here to use the univariate strength as a guide, which is nice because it's also interpretable, right? Because now we show our investigators, look, age is important. It was positively correlated here. It's the same sign in the multivariate. That's really people like that, right? Yes.
So then does that give an opportunity to just inject prior knowledge? Like in this case, the univariate analysis is picking it up from the data, but what's to prevent us to say, I need to make sure that at least one member of this gene pathway needs to be in the final model?
It needs to be, well, certainly you could, but it needs to be, you can just put the penalty to be zero, but you could, I'll show an example later where there is sort of soft prior knowledge you can put in there, like which you would get maybe from somewhere else. Like I have an example later where I get, this is in the GWAS example where I'm using SNPs to measure to predict a phenotype. And we have a small data set. This is with Manny Rivas in DBDS. And then someone else has published a SNP study of the same disease, but they won't give you the data, which is usually the case, right? But they give you the univariate statistics. We use those as a prior. So yeah, you can use, this is just one example of a prior. You could use prior from other data, or if you use your professional opinion or some mix of them, yes. It's a very simple way to inject a prior, right? Most Bayesian methods with priors, they become complicated, non-convex. This is just, you just scale the variables and run GlimNet, so it's very easy. Okay, well, this is interesting. Now, this started off as a project about Lasso. And then we thought, well, what happens? What happens if we have no penalty? So you might remember that, like with Lasso and GlimNet, if you get rid of that penalty, you get least squares, right? If n is bigger than p, and you run the Lasso algorithm to the end of the path where there's no penalty, you get least squares, right? Because that's, you get the first term and the n has gone away. But what happens in this case, if you go to the end of the path? You get something, right? Which I call unireg. Well, this is interesting. It's like a competitor to least squares. Well, here it is, right? We saw this already. But there's no more summation theta anymore. It's just the non-negative constraint. Well, this unireg. So this is like least squares in the sense that you give it data and it gives you an answer. There's no tuning or anything. It's a black box. Gives you a linear model. Well, let's see what happens here to it. First point, despite the absence of an L1 penalty, we still get sparsity because of this constraint. It's really strong, right? If something's trying to go negative, it says, hey, you can't do that, you're zero, right? Okay, so we tried this on a bunch of examples. Let's see, this is a direct competitor to least squares. Well, just to get started, here's an example of we generated data with 300 observations, 100 features, 10% sparsity. And we ran Lasso. And this is going along the path. This is the number of features it picks. Of course, at the end, it gets all 100 features, right? Because least squares, that's what it gives you. This guy, and this surprised me, it never gets very dense. In fact, it's maxing out around 15 when the correct answer is 10. So this non-negative constraint is very strong. It's giving you sparsity without any tuning. Okay, well, that could be good or bad. Let's see more examples. These are all examples which we have in the paper for UniLasso, but here I'm using just for the UniReg, simple regression. The 300 is 100, 10% sparsity. This is the mean square error in the top table, and this is the support in the bottom table. And you can see that in every case, we have lower mean square error than these squares. But the real dramatic thing is the support is dramatically, it's about 1/10, right? They're saying, look, here's a model with only 10 variables that has better mean square error. Right, so I think it's quite compelling. Okay, but this is simulated. So then I went to UCI database, to Irvine. I grabbed all 23 regression data sets, and I get them faced off least squares with UniReg. And this is the mean square error comparison. This is support. I've taken the ratio. So the blue line is when they're equal, and basically it's a wash. They're about the same. Least squares does badly for some reason in 2 problems, but otherwise, but the support is dramatically better for UniReg. It's about 1/3 on the average. So it's averaging about the same prediction error with 1/3 the number of features. So I think this is really interesting because it's, we don't usually get competitors to least squares that are, there's lots of different flavors, robustness and stuff, but this is doing something, I think, somewhat different, right? Because it's using this univariate strength to guide it. Let me pause for questions. So I guess what I'm saying is, again, the last slide has software. This is something you can try, and maybe you should try. Like, you can use cross-validation to tell you how you're doing. And anytime you use LM, maybe this is worth trying as a competitor. Yes.
Are the features that are kept in the support, are they the ones that have larger weights? Like if you look at the distribution of the univariate support,
Yeah.
or their coefficient from the univariate analysis, are they the ones that have larger coefficients?
Well, I didn't check that, but that's going to tend to be the case. Yes, because it's using the univariate coefficients as an explicit prior, right? So yes, they won't necessarily be the actual ones that are biggest, but on the average, yes, you're right.
And the reason I ask this is that in the medical literature, there was this whole idea of what they call stepwise forward feature selection, where you run a univariate regression, you pick the first feature, you take it out, you run it again, you pick the second one, you keep doing till.
Well, that's for stepwise regression, yes.
And this seems very similar.
Well, no, but this is using the unit. See, the first step is the same as ways. The second step, you did a univariate regression of the residual on. Right? This is
Using the information on the first one.
right? Which is again more interpretable because, the univariate guys they're just the correlations with the outcome. So. Good questions.
How well would plain lasso do here? Do we know?
Well, we're plain Lasso do. Actually, we have that in not all these data sets, but we do that in the paper. And again, what happens typically is plain Lasso and UniLasso are about the same prediction error. But this UniLasso gives you way sparser model. So, well, there are cases when Lasso does quite a bit better. You saw the counterexample. So it depends. But the biggest trend is that we get a sparser model with typically no worse error. This is the diabetes data example, which appeared in the original Lars paper. 10 baseline variables predicting disease progression in diabetes patients. And I'll just make the point that actually in this case, I did a whole bunch of sort of half sampling to compare the different methods. In this case, linear and Lasso do better than UniReg or UniLasso. A little bit, they would less than 5% or 10%. But the thing is, one thing that's disconcerting, age, for example, is not a very strong predictor in this data. But the Lasso, for example, picked it, there's 200 half samples. It picked it about half the time, and about half the time the signs are different. I mean, they're right. So you get this model, you say it shows age. This time it's negative, this time it's positive, like it's should bother you, and so. I know I'm criticizing my own method, but that's, it's just a fact of regression, really. Okay. Orthogonal design, okay, so if those of you know about the Lasso and ridge regression, in the case when the variables are uncorrelated, you can write down the solution exactly. There's no need any convex optimization. Ridge regression is just a proportional shrinkage. So you start with the least squares estimates, uncorrelated features, you shrink them all by a fixed percentage, depending on lambda, regularization parameter, 10%, 20%. So that's depicted here. This is the 45-degree line. This is the quite a bit of shrinkage, more shrinkage, more shrinkage. This is proportional. Lasso is a translation. So it doesn't do a fixed proportion, but it moves things towards zero by a fixed amount. So this guy, you say, well, it's really unfair to the big coefficients, right? 10 goes to 5, but 1 goes to 0.5. So that doesn't seem fair, right? Lasso is a little kinder to the big coefficients because it uses a fixed translation. You subtract 1 from everybody, for example. UniLasso is interesting. This was, again, this is merged up from the method. It has its threshold function looks like this. For small guys, it tends to look like the Lasso, but the bigger you are, the more we leave you alone, which is, I think, something quite appealing. And there's other methods in statistics which actually, they aim to get this, but they do it in a non-convex way, which makes it not very computable. So this appealing shape just came out of the 2 steps that you saw in the output. Okay, so this is one slide on theory. And I'm not going to attempt to explain the theorems, but I'll give you an overall picture. First of all, to remind you, you might know this for the Lasso, this whole body of work on when does the Lasso return this, get the right support. So you have an underlying population with support variables, those are ones with non-zero coefficients, and the non-support variables. You ask the question, does N and P get large? When does the Lasso recover at least the right variables and maybe some more stuff? Okay? And there's the general theory says that it's very intuitively reasonable. The non-support features have to be not too correlated with the support features. Right? So if you have a predictor that's, it's got a non-zero coefficient, and another predictor that has a 0 coefficient, but they're correlated to 0.99, you can't expect the Lasso to tell them apart. Right? So, but of course, you have to make that formal, and they've done that. So a lot of different authors and have proven different versions of this. Well, UniLasso, which my brilliant colleague Shorev has analyzed, has a very different support recovery condition. Well, he proves that this one gets sort of obvious. It starts the univariate and multivariate coefficients have to have the same sign for each feature in the support set. Well, that's kind of obvious because that's what we assumed. But a sufficient condition, this is interesting, I think, for this to happen, is this last guy, for each pair of variables in this true support, if they're positively correlated, their population coefficients have to have the same sign. And conversely, if they're negatively correlated, they should have different signs. Which is, if life is fair, this is sort of what you'd expect to happen, right? You have 2 variables which they both point in a positive direction at y. Oh, sorry, they're positively correlated. Then they should point in the same direction. But I mean, we know that's not necessarily true, but it's sort of a reasonable assumption. Right? So again, the philosophy in this whole talk is that yes, some of these things can be violated, but we're making some assumptions to make our model search easier and more interpretable. And we've seen that this can fail badly, like in that counterexample, leading to very bad results. But I think with high-dimensional models, you have more to worry about than these kind of pathologies that can happen. Yes.
Have you tested how this behaves with when one of the variables is missing? So when translating this all the way up to a clinical example, right? There are going to be situations where one of the biomarkers that you need in a patient population is just not available, and so when the univariate coefficients are so heavily loaded, that means each player on the team is more important. And so, does it perform worse if you're trying to adapt it to a missing variable situation?
But I would think it would perform worse. Yeah, because you want to have a teammate on the bench that you can bring in. Good question. Haven't thought about that. But yeah, a sparser model could hurt you in that case. Yes.
it could alternatively, it's empiric. I mean, it could be that it actually is beneficial because the other teammates are maybe even still better. So it's something we talked about testing this in our data. So I think that's something we could actually look at and see how it performs.
Other questions or? I always tell my students there are no dumb questions, so please ask a question if you're unsure of something or.
Was there a motivation for why did you go about this anyway? Lasso's been working pretty well for a long time.
I don't exactly remember how anyway. I think, as I recall, I saw a table like that sign change and that bothered me. I thought, what can I do about that? And it sort of eventually led to this algorithm, which is, yeah. Okay, the simulations, it's always boring to see simulations in a talk, so I'm just gonna summarize them by, I had said this already, that this Lasso, UniLasso tend to have, mean square that's similar. I'd say in high signal to noise ratio cases, Lasso can be considerably better. But again, we have cross-validation to alert us to that. UniLasso delivers considerably, I should say, sparser models. And also, you might think, well, gee, if you want more sparsity, why not just make the lambda in Lasso bigger? Like go back to that. Like if UniLasso has 10 features and Lasso's giving you 20, why don't you just back up lambda to give you 10 as well? We do that in the paper and it does considerably worse. So it's not just a matter of, sparsity. You're getting models that are in very different parts of the model space, right? As we saw in the very first example, these are very different models. It's not like I can tweak the Lasso a little bit, get this model. They're very different.
We have a question online from Steve Goodman, if I can go ahead.
Oh, sure. Really, really cool stuff. Also, looking at where it's strong and where it isn't. Just wondering if you tested this out in other than least squares settings, other models.
We have, we've got software for all of the GLMs and COGS models, and we've used it in many different settings. Yeah.
And does it qualitatively behave differently, or is it always, behaving much as you've described here?
I wouldn't say always. Yeah, it's got generally the same behavior, although we haven't tested it as much in other models, but so far it's very similar.
Okay, thank you.
Thanks, Steve.
Then Brian Money had a follow-up question as well. Brian, go ahead.
Yeah, thank you. This is the second time I've heard your talk, and I think I needed 2 or maybe 3 times to get all of it. But
Okay.
no, it is. It's very I think you make a lot of these statements, but do you see any reason why someone using the Lasso shouldn't instead default to using the UniLasso? Maybe with the caveat to look closely at cross-validation for the setting it doesn't perform well in. Like it seems like it's just a strict improvement as long as you're not in this that one setting.
Well, not even the one setting I showed. There's other examples in the simulations that Lasso does better. So I would never say you should replace Lasso by UniLasso. I would say you should try them both. It's so easy to do, right? And look at the cross-validation there, look at the model you get now, just use your judgment. But in many cases, it'll be an improvement. And I have a lot. You asked that about a list of collaborators at Stanford that are already using this in the medical school, and they like it. It's giving the models that predict well, they like to interpret them. So that to me is a real test. You can always come up with simulations, but when real scientists like it, that's a really good sign, I think. Yes.
I agree. And this is the second time I've heard it, and I agree. It's nice to hear it a second time. I'm really trying to absorb it. Because I just was thinking about another smaller comment, which is that for a clinical application, we also think about modifiable factors, right? So if one of the elements in the list is modifiable, it's helpful to be able to tell a patient, if you move your LDL, if you move whatever it is, it's going to, I can expect that it will have this effect. But if your model has sign flipping, I don't know actually which way will help you in this particular example. And obviously LDL is not maybe a great example because we know, lower is better, but that may not be true for all biomarkers that are intervening.
Very good point. Let's get this talk again. Okay, so this is actually what I was referring to when Nick asked the question. So this is variation on this, which Megan already anticipated, which is using scores from somewhere else, the products, right? So this is again this is simulated data, but I've been talking to Manny Rivas, who tells me this is quite realistic, that again, in the SNP world, using SNPs to measure, to predict some phenotype. And, you know, Stanford's sort of a small place. We have fairly small studies. Maybe you have, 60 patients or something, and you measure their SNPs. Someone else's from Sloan Kettering has done a much bigger study, and they've looked at the same disease with SNPs, and they've got way more data, right? But they won't give you the data. This is typical, because maybe it's not surprising. It's worth a lot of money and effort. But they do publish like the t-statistics for each feature, right? Well, we can just use those, right? Instead of internally obtaining them from the data as we've done, we just use those. So the question is, does that work? But here's a simulation to examine that. I generated data with about, I think, 500 features. I don't have them on here. In normal data. And here's the test mean square error for our two methods so far, Lasso and UniLasso. So far, there's no use of any external data. This is just straight pruning. Then I said, okay, suppose we have this external data set E. That's the data set from Memorial Sloan Kettering. Big data set. But we don't have access to E. We have access to the scores. It's the univariate scores. So what I'm going to do is here, for example, I took our data and I added 100 scores from E. I use that as those priors. And you see, you get an immediate, pretty good improvement in mean square error. To my surprise, I haven't figured this out. When I add more scores, it doesn't really help. I don't know where that is, but then if I steal the data from Sloan Kettering and I do much better. Not surprising. But I think this use of as a prior is pretty interesting. We have lots of other cases where you could get prior information from other sources and express it very simply as a t-statistic. Yes.
Yeah, that's where my mind is going, that priors from other sources. I mean, there are certain features that are druggable, there's certain that are cheap to measure.
Yeah.
There's other costs attached with them, and if that information can be fed in, we get a more valuable model, even if it's for like that. Accuracy performance might be 2 points lower.
So you're saying you should take into account how expensive they are to measure?
Right. And certain measurements are more expensive, some are cheaper. If I'm building a diagnostic, I want cheap measurements.
And you also put in your prior belief of what the strength of those things do. Yeah, that's a nice point. Okay. I'm going to go there. So I'm basically done. I'll say I'm really quite hot on this univariate idea now. And I've got students working on random forest and neural networks and boosting, all with the same theme, right? They're all doing model search. It's difficult. As you mentioned the random forest example, where you keep deleting stuff in it. But we have ways of injecting univariate information into them now, which I think should help them too. And especially neural nets where the objective function isn't even convex. You've already got a problem with local minimum. So it needs more help. Maybe the univariate guidance will help that method too. We haven't got that working yet, but it's in the works. Oh, as I mentioned, here's a bunch of collaborators, some at Stanford, some at other places that are using our software, and they seem to really like it, and they've given us some good ideas and data sets.
Wait a minute, even your collaborator has been to 2 talks and still trying to figure it out. This is what I keep using.
That's great. Okay, and here's, so if you want a screenshot of this.
Oh, thank you so much.
So this is the paper. This is the R library.
Are there any access limitations?
No.
Okay.
And this is student Sophia Liu, another brilliant Stanford student, has done a Python implementation.
And in return, I'll give you a little tip also. So I did like a SNP analysis using GWAS in Pittsburgh, and during my fellowship on a gene called as beta-2 glycoprotein.
Mhm.
And the reason why it's very hard to share the data is because we usually plot it as a plot. Like when we report it in a paper, it's like, for example, interferon maps and
Yeah.
signaling pathways in clinical medicine. So it's really hard, but Pitt has got like a very big database. Northwestern has got like, so maybe like
That's a
sharing.
good source for you.
Yeah, you could, maybe collaborate with them to get more numbers because my study had over 300 systemic lupus patients. And we were trying to assess if there were any pathways or any SNPs that were relevant for plotting disorders in that patient population.
Okay, thank you.
Okay.
Question in the back.
My question is about, you mentioned we need to have the same sign. For example, in the Lasso, we have for some features, we have negative signs or positive signs.
Yes.
My question is that in some domain, we know, for example, the association of some exposure with respect to some diseases, how we can realize when you consider a univariate analysis, the score and the sign is more related to the data. Maybe by changing in different data sets, we can see different association between one feature and outcomes, more dependent on the data. But when we have a compositional effects, when we consider multivariable coefficient values, when consider multiple features together, these association a little bit is stronger than the universe. How we can trust on the sign that you mentioned, for example, positive or negative, depending on the domain that we are working on. I mean, the compositional effect of the features can be seen when we consider the multivariable, for example, analysis. But in the univariate analysis, depending on the data sets, maybe, I don't know, can we find different associations and it's not so reliable? I don't know, maybe I'm wrong. What do you think?
I'm not quite getting your question. I mean, of course, it's true that you have different data sets on the same disease, and the univariate coefficients might have different signs in different data sets. Is that okay? So that's true. Maybe ask your question again. So that can happen. Yeah.
I mean, you mean we should select one sign, we should have one sign, the same sign for example, in our model.
Well, I've only got one training set here. So you're saying I have multiple training sets, and in the multiple training sets, the sign of a given variable might be different. So you're asking how would I sort of?
Yeah.
Well, I mean, one could just concatenate the data together, get a bigger data set, and use its sign, which is sort of, you could, right? So you'd get a more stable estimate of the sign with more data. You combine all the data together and use that as a training set. I'm not sure if that answers your question.
Thank you.
Maybe we could talk later.
Yeah.
Great, well, we're pretty much at the hour. Why don't we thank Dr. Tibshirani for telling us his latest methods, and really appreciate it. And follow up with more discussion detail for people afterwards. Rob's very open. Thank you so much, everybody, and we'll be back again next week.